around the 80s. And you guys, your class actually asked about it. I think the other class just ignored it and said, whatever, I don't think it's important. Which at the time, it really wasn't. It wasn't on the test, etc. But I want to talk about this really quickly. Probability, just a few ideas about it, okay? And why on earth it's in chapter 9. So in the directions is where it started to teach probability to you. It said, hey, guess what? If you were repeating n trials, and technically I guess I could do this on the smartboard so that anyone who's absent today would be able to access it. Let's go back here. Okay. If we were to do n trials, where you had p successes, q failures, and k was the number of desired successes. It told us in the directions that we could figure out the probability of successes using the formula NCK ultimately Q the n minus k the k. What does that look like? Binomial theorem. So probability actually applies binomial theorem. And let me give you an example. And you guys had some, I think, in your homework as well. And you had a question on it. So let's just try to make this a little more real. So for instance, if we were flipping a coin, let's see, 10 coin flips. And your options are either heads or tails. What do you guys want to call successful? Getting a head or getting a tail? Doesn't matter. Okay, getting a tail. So we'll say this one is the successes, so we'll call that one P, getting a tail. And then we'll call this one, well, it's the failure, right? You don't get a tail, you get a head, so then that would be the Q, that would be the failure. If you're flipping a coin 10 times, a success is a tail, a failure is a heads. What if I was to ask you, using that idea, how to find the probability of getting exactly 4 heads? Now, I don't care in what order. Sorry, not 4 heads. I apologize. Success is tails. 4 tails. Probability of getting exactly 4 tails. Okay, so getting exactly 4 tails. What can we plug into this formula? 4 is going to be plugged in for what? Good, the number of desired successes, so that's going to be my K. So I'm going to have my C. Who's my N? How many trials are we doing? How many attempts? Good, 10 attempts. We're trying to get 4 of our successfuls, 4 tails. Now, we'll get back to who is P, who is Q in a second, but 10 minus K, 10 minus 4 is 6 of those and 4 of those. In here go not the number of successes or failures, but the probability of a success and the probability of a failure. So what's the probability of getting a tail? Oops, nope, that's failure, right? Of getting a head. 1/2, 1 out of 2. 1 out of 2 outcomes is going to be a head. And how many percentage odds of getting a tail? 1 out of 2. So this is how you would plug in to figure out, and we could, how would we plug this in? We could use the formula, or we could use NCR in our calculator, right? Math and probability. So we would go ahead and calculate. Why don't you guys go ahead and calculate that real quick, and let's make sure we can do it in our calculator. And then let me go ahead and try to introduce you to why probability gets hard. This is hard in and of itself, but how it gets more complicated. Or you have to put the number before NCR. So you have to put the N before, type a number, then NCR, and then R goes after. Okay, so what do we get? 0.2. Keep going.
It's actually 0.205.
Okay. 0.205, which would be 20.5%. Did you see it? Okay, so you guys agree with 20.5%? Okay. Now, that one we were able to totally fill in because we knew that the probability of getting a heads is 1 out of 2 and the probability of getting a tails is a 1 out of 2. Now, as soon as we get something a little more complicated, this idea still would apply, but just be a little bit trickier. For instance, let me go ahead and use for you guys the same example I used in period 2, just because I'm not sure anyone else in here would know how to fill in the numbers. We were talking about, because I was asking, hey, what are some other examples where you either have a success or a failure? There's no like in between. Michael Gerges was like, oh, hey, if you don't know like the gender of your baby before it's born, you have a 50% chance of getting a boy, 50% chance of getting a girl. Okay, kind of, but we know that there are some biological issues that can occur that make that a little bit more tricky. So I was like, yeah, let's not use that one. Then someone else was trying to come up with other examples. Can you guys think of anything where you either have a success or a failure, like there is no in between? Like a yes or no. So like a heads, yes or no. And that's the only types of options for a coin. What's another yes or no type of trial? Confess and propose? Oh, proposing, you get a yes or a no. Yeah, that's true. If we were to use proposing, number one, hopefully you're not proposing multiple times. That would be a little awkward. But number two, we would need to figure out what are the chances that the person will say yes or the chances the person will say no. Is that something we can really measure? No, because proposing, the person hasn't been proposed to tons of times in the past. They're a different person, theoretically, so then the chances would be different. So that'd be pretty complicated as far as actually figuring out the odds that someone would say yes or no. Truth or dare? I mean, they can either choose truth or choose dare. Once again, it'd be kind of hard to figure out the probability, like, does this person tend to choose truth? Does this person dare? You have to do tons of different trials with very similar questions, or else they're like, well, it depends on who they're playing with, whether they choose. Okay. Something else. Is there anything that's measured as far as probabilities or chances or stats? Oh, there we go. That's what I was waiting for. Are there a lot of stats in sports? Why? People care about how they perform, and people care about gambling, and people care about their teams. Some combination of the above, right? The players care about how they perform, so do the coaches, so do the owners, et cetera, in order to build up their franchises, et cetera, in whatever sport you're in. So like the people that have a vested interest, they care. People that gamble have a vested interest because they care about knowing the odds. Like we just went through March Madness and people's brackets, right? Some people just randomly chose their brackets, and some people were very particular about who they chose and why they chose them for reasons beyond just the, I like their colors, I like their mascots, okay. A lot of people actually know their stats, and we're actually trying to do this in a strategic way. So in sports, there are a lot of stats. So here's what we ended up doing. We ended up doing, because Noah's in our class in period 2, we ended up doing free throws. If he was practicing free throws and he made 25 shots, okay? Free throw line, he's practicing 25 shots. If Noah made 25 shots or did 25 attempts at a free throw, the free throw is either a make or a miss, right? It's either a make or a miss. And obviously, what would Noah think was a success or successful? A make, right? So we're saying, okay, if he got the bucket or if he didn't get the bucket. So then we were going ahead and saying, okay, what's the probability of him, they wanted at first to say of him hitting all 25. Okay, start plugging in for me. What will we plug in? N is, okay, 25 different shots. C, good, because he's supposed to make all 25 of them, so that's going to be our K. That's going to be our N, right? Now, here's where it gets to be a struggle. This one will be 25 minus 25, so 0 misses and 25 makes. But here's the struggle. What do we plug in for probabilities? Does he have a 50% chance of missing and a 50% chance of making? If you've seen Noah play, no, it's different than that. So then I asked him, I'm like, Noah, what's approximately your free throw percentage? Did he know it? Yeah, he was like 88% about. How does he know that? Could he have just guessed? Yeah, if I asked one of you guys, you're like, 12%? Yeah. Like maybe, or maybe you have 95%, I don't know. But you probably would have to guess. Why? Because there hasn't been repeated data in order to actually accumulate and to see and to calculate what your percentage is. But roughly, Noah's been playing basketball for a long time, club and then school, and he knew approximately his average is 88%. What would we put in for the success category? 0.88. What would we put into the 12? Why? Has to add to 100%, right? So if it's 88% making, it must be 12% missing. Now, plug this one in. Let's see what you guys think. If someone were to guess right now, he has an 88% free throw average, and then making all 25 shots. Does anyone want to even? Period 2, I think Nick Haritonian was saying 40-ish. What does the math say? About probabilities, not what's going to necessarily happen. 4.1%? It's not very high. Weird, right? But if he has an 88% free throw average, what's the percentage of him missing 1 out of 25? Pretty high. Now, we were like, okay, hold on. 25, okay, that was a little unrealistic. He's good, but is he that good? If he's an 88%, which is really high, I mean, 90s, in the 90s would be a lot better, but 88% is pretty high. Okay, yeah, I get it. He could miss one. Like there's a high probability he'll miss one. So then we're like, okay, let's check out what if he only needed to hit 20 out of 25. So probability of hitting 20. Okay, what would change? 20 goes where, though? In the K spot, right? So then how many shots would he miss if he hits 20? Good. So he's going to miss 5. 25 minus 5. How many is he going to make? Okay, let's throw that in. Let's see what that one's going to be. And some of you are like, okay, now my 40%, 50%, 60%, that should make a little more sense if he's hitting 20. But wait a minute. Hold on. 0. Hitting 20? Doesn't that seem weird? But here's the dilemma. This formula is 20. So hitting exactly 20. Not 21, not 19, not 24, not 23. What would be a little bit more practical? Well, what did you guys do with the stapler? Test corrections? Oh, thank you. Thanks, guys. Coming back. Only 10.3% chance? Yeah, but that's because maybe he hit 21 or 22 or 23 or 24. Wait a minute, hold on. What word could I put in the question that would make me consider the 20, the 21, the 22, the 23, the 24? Not just hitting exactly 20, but hitting at least 20. Yeah. Because 20 would be good, but wouldn't it even be better if he hit more than that? So, okay, when we're thinking about probabilities, you have to think about, even though you're like, oh, that could happen, it could happen, but what's the odds he only gets 20 and doesn't get more, doesn't get less? This one hitting all 25, we saw that was a small percentage. Hitting something that's lower, okay, he has a higher chance of getting it, but still hitting that 1 and not hitting a little bit above or a little bit below. But instead, if you were to say something like at least, well, hold on, but if it was at least, wouldn't we have to figure out the probability of getting 20? And 21, and 22, and 23, and 24, and 25. What would we do with all those probabilities? How would we put them together? Just add them. Yeah, we would just add them. So this is introducing the idea of probabilities, the idea of chances, the idea that they don't always follow what we naturally think or what we naturally try, what we would naturally assume or we would naturally guess, hence why people in Las Vegas make lots and lots and lots of money. Not the people gambling, but the actual casinos. But coming back, What you naturally think, there might be a very small percentage or a very small probability that it'll actually happen. Doesn't mean it'll never happen, but it means that it won't happen very often. And what we naturally think, the probabilities not always follow what we would naturally say. But there's also a lot of complicated things as far as the difference between exactly and at least or at most. So there are some things that we're going to have to be really careful with when we're even reading problems. Now guys, section 9.6, let's go through this example real quick. If you want to show it in your notes, you can. If you don't want to, that's fine too. You guys good?
Yeah,
Just need notes.
Can I take that back? For high school, I made them stickers. And if you got geometry, she got a sticker.
Yes, you can come grab this for high school lunch. All right, kiddos, I want you to go ahead and read the example. Try to answer A and B. You can discuss it just a little bit as I write these guys' passes. Katrina, can you pause my video? All right. What have you guys figured out? Can 1 through 8 be repeated? Not as far as the number of pieces of paper, but how many are you picking out? No. You draw one, then you draw a second. Okay, so you're just drawing out 2. You can't just like go and pick them all and be like, yay, I got all. Okay, so you pick out one, you put it back, and then you pick out another one. Did we get that? Okay. Only the numbers 1 through 8. Oh, just the 2 pieces. Perfect. So you only have the numbers 1 through 8. They ask, how many different ways can you obtain a sum of 12? Okay, you guys are already thinking. You can do 4 and 8. That's one pairing, right? What's another pairing? Okay, if you have 6 and, ooh, that's possible because what happens to the 6? You put it back in, so you could theoretically get it again. And then what's another possible pairing? 10's going to be too big. 7 and 5. Okay, so there are 3 different pairs of numbers that would work. 4 and 8, there's a 4, there's an 8, there's a 7, there's a 5, there's a 6, there's a 6. But is that the same answer, 3, for letter B? No, because couldn't you have pulled the 4 and then pulled the 8, or pulled the 8 and then pulled the 4? Those would be 2 different ways, 2 different draws. Does that make sense? So there's going to be 2 of these, because it could be 4 and 8 or 8 and 4. There's going to be 2 of those, 7 and 5 or 5 and 7, but hold on. You pick out the 6, and you get the 6 again. Is there 2 ways of doing that? No, there's only 1 way of doing that. So therefore, 2 different ways of, 2 different ways of, 1 different way of. So that'd be 5. Does that make sense? 2 different ways, and then 1 different way. Now, why were we able to actually count all of these up? Because it was only numbers 1 through 8, and we know how to add to 12, and there weren't that many options. What if I was to say, all of a sudden now in the box there's numbers 1 through 47. Why? I don't know. I just randomly came up with it. 1 through 47. And how many different ways could you pull out 2 that add to be an odd number? Because I didn't even just tell you like 21. I said any odd. Oh, stink. Well, how many ways to get 1? How many ways to get 3? Can you get 1? No. How many ways to get 3? How many ways to get 5? Oh, that'd be rough, right? So here's the idea of section 9.6. Section 9.6 says, yeah, we better talk about not just how to actually, look at a problem and figure out all the ways and count them up ourselves, but how to actually maybe have some principles, formulas, or other clues to help us, because these numbers are going to get big. Now, wait a minute. Hold on. Weren't we just talking about probability and how the numbers were actually really small? 0.205, 0.041, 0.1025. Does anyone have their book? Can you turn in the back to the odds? I'm going to turn in the back to the odds. No one has their book? Not one person? Ah, there we go. Jack has it.
Oh, of course he does.
Jack, turn to the odds. Section 9.6 and 9.7. I'll hold it up for the kids that don't have their book. 9.6 in the odds and 9.7 in the odds. Kiddos in the front. I want you to look at 9.6 odds, if you can see them. How big are the numbers?
Pretty big.
How big are the numbers? Whoa! 5,586,853,480. Anyway, they're big. They're millions and billions and thousands. You guys in the back, you want to see it? Section 9.6. How big are the numbers? They're big, right? All the way from the front. The numbers in 9-6. Yeah, these are like the odds, right? The numbers are big. You have thousands and you have billions. And okay. Now pause. I'm going to go backwards. Check out 9-7. What do you notice? They're fractions. And the fractions are going to be little baby decimals, right? 9-7, all of a sudden they're very small. Oops, sorry, Jack. All of a sudden they're super small. They're fractions. So what's the difference between 9-6 and 9-7? 9-6 is saying how many ways can something occur. 9-7 says now take that out of the number of ways possible. Make a fraction, and there's your probability. So 9-6 is not asking for probability or odds or chances or any of that. It's just saying, do you even know how to count up how many ways it could possibly happen? Because that can get really overwhelming. So check it out. On this one, if I was to ask you for the probability, which is going to be section 9.7, the probability of getting the two numbers that sum to be 12. The probability of getting two numbers that sum to be 12. So I can say getting a sum of 12. Now we have to take that 5, and then we'd have to say, what do I put it over? 5 is how many ways this can actually happen. Over, well, what are all the different ways of picking two numbers? We would call that the sample space in section 9.7, but we'd say, okay, how many different ways can you pick? How many different ways can you pick two numbers? Well, kiddos, can anybody think of how we would figure that out?
8.
Not just 8. That's how many ways to pick out the first number, right? 8 different ways to pick the first number, but then you also have to go ahead and pick the second number. So let's say you pick the 1. How many different ways can you pick the next number? 8 different ways, right? So there's going to be 8 different options for 1, because 1 could go with 1, 1 with 2, 1 with 3, 1 with 4. So there are 8 different options for 1. Okay, how about the 2? 8 different options. The 3, 64. 5 divided by 64, that's a probability. That's a chances of. Those are the odds. So before we can ever make the fraction, don't we have to figure out how to find these two numbers? That's section 9.6. So we're not going to probability yet, even though it would be 5 over 64. That's what's coming right now. We just need to figure out, can we count up how many ways, or else we can't make fractions. So let's go ahead and start here. Sometimes we can use logic, and sometimes we'll use some fundamental counting principles, some formulas, and some other clues. So here we go. Let's see. Is this one that we need formulas, clues, or can we actually just kind of do this in our head? We have a computer randomly generating numbers 1 through 12. We'll assume the numbers can be repeated because the computer is just kind of spitting them out. So if it's random, it can technically throw out a 3, throw out a 3, throw out a 3, a 6, and 7, a 9, a 3, a 3, a 3. The numbers can be used more than once. Oh, but it's just spitting out one number, because number 11 says it's just going to pick one number. What's the, not the probability, but what are the number of ways, or how many ways can a computer spit out an integer divisible by 4? Tell me which numbers are divisible by 4 in that range. 4, 8, and 12. Oh, so how many integers? 3. How many ways can a computer spit out? 3. Now, what would be the odds that it would, or the probability? That's section 9.7, but you would say, oh, there are 3 that fit that condition out of 12 total possible. So your probability would be 25%. But for right now, we're just saying, oh, there are 3 ways that happens. Now, hold on. Number 13, sum to be 9. Okay, well, hold on. Distinct just means 2 different. You can't have the same number add to be 9, but it's okay. 4.5 and 4.5 aren't even legal, because what did it say about the numbers? Integers. And integers mean no decimals, no fractions. Okay. What are some numbers in between that range that add to be 9? 5 and 4. 6 and 3. Couldn't you have gotten 4 then 5? 3 and 6. 7, 7 and 2. Any more? So we have 2, 4, 6, 8. So we have 8 different options. 2, 4, 6, and 8. 8 different options. Does that kind of make sense, kiddos? Okay. So these ones we were able to logically kind of contain all the information and go with it. However, you're going to write this down. Just hold on, hold on. Can you look at the example just real fast? Do you want to actually list out all the different possible pairs of letters from the English alphabet? Why? A could go with A could go with B, A could go with C, A could go with D. Ooh, B could go with A, B could go with B, B could right? We're not going to hold all that in our heads. Now, some of you can make mathematical deductions on how to actually solve. That's what this paragraph is for. So go and get this down. Let's talk about a principle that we can use to simplify and not just have to be like, well, if my brain can see it, I'll get it. And if it can't, oh well. There are some strategies, and here's one of them, the fundamental counting principle. The fundamental counting principle. I want you guys to think of, if you don't already know, how many letters are in the English alphabet. 26, good. So just using the strategy up here, we would say, okay, we have 2 different letters that we're choosing. Now, if you guys notice, this word and is going to go along with multiplication. And in probability goes along with multiplication, but only when you're using it to discuss 2 different outcomes, 2 different events. Not 2 different, like they can't be the same, but 2 different as in 2 distinct outcomes. Let me give you an example. If I was to say something like, what are the chances if I were to randomly choose a student in this class that they would be a junior and a boy? Okay, that means one thing is, like, one student's being chosen. 2 different characteristics that are true, like a Venn diagram kind of, like all the boys, all the juniors, okay, how many overlap are there? So if I said and, like one person, 2 characteristics, that's one use of and, but this one is like, no, you're doing 2 different things and you're putting it together, like you're choosing letter 1 and letter 2. Does that make sense, the use of and? It's not like 2 characteristics about one object, it's 2 different, in a sense, objects. So, question, how many ways, M1, how many ways can you choose the first letter? 26. How many ways can you choose the second letter? Yeah, because they don't say that it can't be repeated, so 26. So the final, how many ways, how many pairs, would be, I think, double check me, is it 676? Okay. Now, hold on, let's think about it this way. If you were to list all the letters A through Z, 26 of them, and if you were to say A could go with A, B could go with A, C could go with A could go with B, B could go with B, C could go with B, etc., wouldn't you have 26 this way and 26 that way? Think area. If you have 26 and 26, what fills in? Multiplication. So maybe that helps a few of you with what's going on. If you were to list them all out in a strategic way, yeah, you would get 676, but it's a lot easier to do this. What if there are some characteristics that have to be met? Meaning, maybe we're picking more than 2 letters. Maybe we're picking numbers. Maybe there are some things that can or can't be true. And this one, you guys can write the whole paragraph, or you can summarize the most important information. I need a license plate with 2 letters and a 4-digit number. Or you could think of 4 single-digit numbers. Either a 4-digit number or 4 single-digit numbers. Now, the letters are easy. Do they say anything about not being able to repeat the letters? No, but ooh, what do they say about the letters, guys? O and I can't be used. O and I can't be used. So how many letters are legal for me to choose from? Good. But I can repeat them. They didn't say I couldn't repeat. If I couldn't repeat, this wouldn't be 24. I just used a letter. Now I'd have 23. But since I'm allowed to repeat, good. Okay. 4. Think of this different ways. So some of your brains, you might want to think about this as, it's not letting me, oh well. Let me show you the easy way first. The easy way is to think about them single digit at a time. How many single digits are there? Careful. Why 10? 0 through 9. Good. So 1 through 9, there's 9, but 0 is also an option. So there are 10 different options, 0 through 9. Well, wait a minute. They didn't say I couldn't use 0 or 1. They just said don't use O and I. So, well, how many options are for the rest of the digits? Didn't say they can't be repeated. So I'm going to end up with 24 times 24 times 10 times 10 times 10 times 10. Now, some of you, this makes sense, breaking it down digit by digit. Others of you, it's a 4-digit number. Go from 0 to 9,999. 1 to 9,999, because how many, if it was like in the thousands place, 9,000 is the highest I could go. That would be 10,000 numbers with the 0. So some of you could just come up with the 10,000 on your own and say, oh, there's 10,000 4-digit numbers times the 24 squared. And that would also be okay. You could kind of like group this all together as how many 4-digit numbers, or you can just think of, oh, multiply digit by digit. Did anybody actually solve that? Cool. Does that make sense? Okay. So, this just doesn't like me. Question. How many blanks am I going to put for this whole scenario? For each one, because they're all kind of a little bit different. Good. So go ahead and make your 3 blanks for the first one. We're making 3-digit numbers. Let me see if I can get this to work a little better. Nope. Nope. Okay, we're just going to zoom out and for it. The first one, leading digit can't be 0. Ah, if it can't be 0, how many options do I have? I have only 9 options. But how many options do I have for the 1s and 10s place? Do they have anything to do with the leading digit can't be 0? So some of you might have thought, oh, hey, all the numbers 100 to 999, maybe you would have figured out 900 different options. But maybe taking it blank blank will help. Kiddos, thanks for your patience with today. I know it was a crazy one with everything going on. We'll catch up tomorrow. We're just a little bit behind. Starting 9/6, that homework won't be due until Friday.